Dang. All right. All right. So by the system schema, what's one interaction that box A is experiencing? An interaction with box B. Which way should that point? Which way is A feeling a force from B? Hayden says down. You agree with that? Okay. What is another interaction that box A is experiencing? All right, Hayden's on fire. I don't know about the rest of you. So we've got gravity acting here as well. That's the gravity to me is the easiest one to draw, right? Because I just know it's mass, so I know a gravitational interaction with the Earth. It's 100 kilograms. So there should be, I'm going to make that a bigger arrow, right? Fg, that's 1,000 newtons. Now, what I'm not doing a good job of is labeling this. This should be A, comma, Earth. This should be B, comma, Earth. This should be B, comma, what? B? Sorry, if you look over here. Yeah, A is the thing that's pushing up on B, yeah? Okay, so I've got 1,000 newtons of gravitational interaction that is acting downward on A. Hayden points out that A and B are interacting, and then Josh and A are interacting. Which one of those forces is more of a dead cert right now? Which one do I know? Josh, right? It tells me that Josh is pushing on that one. I want to direct that up. That's 1,300, right? That should be a big arrow. That's smoosh poosh, A, comma, Josh. Now that makes it look like there's 300 newtons of unbalanced force on box A. But I already established that the FU should be 130. So there must be something else acting here. So this is where I need the deep thinking, because this is like 2 or 3 essential understandings going on right now. What else is acting? How much is it? Why should that make sense? That's what I need to run by your neighbor. So here's all the stuff I'm asking you to make sense of right now. We've identified the FU for this box should be 130. Gravity is 1,000 newtons down because this thing's 100 kilograms. Smoosh push is 1,300 newtons up because it says that's how hard Josh pushes on the box. Hayden pointed out that A and B are interacting, so you know what the other interaction is due to. But how does that all come together here to give us an FU of 130-ish? And I think that's where my problem was, right? Because this is 1.33323. So we're going to be in the ballpark of making sense here. But if and only if you're kind of paying attention to what we're doing. Or at least having the sheet out in front of you so it looks like you're pretending. So somebody help me out here. The interaction that A is experiencing from B, is that pointing down or pointing up? Where are you at? Come on, old school pair deck. The force that would be called smoosh poosh A comma B is pointing out. Okay, down, right? So that's F smoosh poosh A comma B. And so if I make some more space for myself here and draw the force addition diagram, I've got 1,300 newtons up. I've got 1,000 newtons down. That's the FG. How does this work? Should it be like that much? Or should it be like that much? So I need you to kind of make sense of the tools that we have here. And think about the motion that we've discussed and described here. Should that arrow finish above the dot or below the dot? In other words, should it be a this or a that? Okay, so have a go at that right now. Use the tools and try to make sense of things. You're halfway tuned in. There's a nice little thing that's happening. You're sitting there wondering why nobody gave you a Valentine today. A, that's sad. B, that's not going to help you do well in the quiz tomorrow. I'm asking you to wonder why I wandered around trying to find the pair right there. Let's give them a this or a that. We said the acceleration is 1.3 or 1.333. The FU's got to be 130. If it's an upward FU of 130, and this is 1,000, and the total's got to be 1,300, that would mean 170 for this little guy. Okay? If instead it's a downward FU of 130, this whole thing's 1,300, that's 1,000, where would we be at for this force? The do math. I need something to click for you, but if you're just standing there holding your fingers, it's not going to click. If the FU is 130 up, that means the interaction from B is 170. If the FU of 130 is down, what would this whole thing have to be? Do some math.
170 plus 130 is 300.
Plus 130 is. Okay? Did you catch what Hayden just did there? Right? These numbers are right here for you. 170, 130, 130. Adds up to 430. What's the significance of getting a number in the ballpark of 430 for a force that's called A, comma B? Bronzer? That's pretty much the smoosh boosh over here, okay? We didn't take this out an extra digit, but if we'd gone 1.33, maybe we'd have a little better agreement. We said that B feels a force upwards from A. That's about 430 newtons. So that's how it works then. A is going to feel a force from B downward about 430 newtons. Okay, so now I can go over into my diagram, and I know that this smoosh poosh here is 430 newtons. How many newtons is the force that B applies to block A? So that would be the force B applies to A is the force that A feels from B. I'm going to put squigglies because it's approximately 430 newtons, okay? And that's approximately equal to the smoosh poosh that B feels from A. That's force pairs. That's like essential understanding 5.7. And then there's some information down here in the bottom. The bottom of the block A starts 2.2 meters above the floor. It's initially at rest. How high above the ground is block A 1.3 seconds later? So it starts at rest. Again, and I can't remember who it was that will credit with this from yesterday, but recognize if it says it starts from rest, your velocity time graph starts at 0. It starts out 2.2 meters above the floor. And then we want to know, where is it 1.3 seconds later? It's falling, so technically we should probably go like that. But that's 1.3 seconds. And hey, by the way, we know the slope of this thing. 1.3 meters per second squared. So how does math work? .3 meters per second squared equals what divided by 1.3 seconds? That's almost handy numbers. And I should probably technically be treating this as negative 1.3 because that's a negative slope here. I'm just being lazy because it's a Thursday, but I think it's a Friday because I haven't been at school 2 days in a row for 3 weeks. So I'm getting like 1.7 meters per second, but that should be negative because of where I'm at. And then I can figure out this area here equals negative 1.7 meters per second times 1.3 seconds. I get negative 2.21 meters there. BG's raising his eyebrows. How about you? Whoa. Peyton looks like somebody just fed her peas for the first time. That face you were making. You don't know that face? Why can't I just... It's that face. Whoa. Pretty much, right? Preguntas, responsos. What I do, you're just, come on. You need a little engagement on Thursday.
Made a mistake.
Yeah. It was thinking that you were paying attention. Class. This is a mistake. I didn't catch myself making it until I was in it. But what do I need to do? Your equation's wrong. What's wrong? What'd I do? Because I'm dealing with what here?
Powering off.
Because I'm dealing with what here? Of a...
Triangle.
But specifically, why do I want to add the half? Because it's a triangle, okay? So I derped because it's a triangle. So I need to divide this by 2. So that's going to be, who's got a calculator? Negative 1.1 meters, okay? So it starts off 2.2 meters off the ground. It's going to fall 1.1 meters. So after 1.3 seconds, it's 1.1 meters off the ground. What is the velocity of block A and B at this time? Negative 1.7 meters per second, okay? So that's the size of those apples. So my answer for how high is it off the ground is 1.1 meters, because what I calculated was the change. The change is negative 1.1. That's not what it's asking for. So if you put negative 1.1 here, that would be wrong. 2.2 minus 1.1 meters, that's how high it is off the ground. Not how fast is it going, what is the velocity? That's why it requires a negative sign. The blocks are probably connected, so ta-da, ta-da. All right, so that's what's up with that one. All right. On a somewhat related note then, I want to take you over to this thing, and I got to power this thing back on.
Powering on.
And I don't like that sound.
Let's say Jack holds both balls.
What up? Tomorrow's just a BF or UBFPM quiz. Yep. Yeah, because we got the end of the try pushed back.
And then he drops them at exactly the same time. What do you expect to see?
Well, they're going to hit the ground at the same time. I expect them to both land at the same time.
Same time.
Well,
I think they both will.
This one to hit the ground first. However, they would actually both hit the ground at the same time.
Why is that?
Science.
Yeah, science.
Now, the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed. From this height, yeah, pretty much. Just constant speed all the way down. Speed?
Yeah, I think it'll be the same constant speed.
I think it's constant.
I seem to remember it being constant. I did decently in physics, and I seem to remember that's the answer.
Whereas the truth is, the speed of both balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar in terms of gravitational pull. They're both at the same and they'll fall at the same rate. I'm not like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull and you've told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is heavier and has more gravitational pull. But when I drop them, then they get equal with gravitational pull somehow.
Don't you think it's going to be like 5 times as much?
Yeah, you think, but it's not.
The way you're asking it, yes, but scientifically speaking, no.
The gravitational force on both these balls are the same.
The gravitational force on both of these balls is the same.
Is that what you actually believe?
No, but it is.
Tell me what you believe.
I believe it should be more on this, simply for the fact that this is heavier. And just intuition tells me that it should be more. But after learning physics, we learned that it is actually the same.
I actually think the force on this ball is more than the force on this ball.
No, you don't.
I swear. I am not trying to mess with you. So,
Like in real life?
in real life and in physics, I will tell you that the force on this ball is more. All right, ready? 3, 2, 1.
Yep, see?
Same time.
They lost at the same time. I would say the force on the medicine ball is like a lot more because it's got a lot more weight, it's got a lot more mass, but it's got a lot more inertia.
Ooh, he swore. All right, so I have to hear the dirty words. So you can see this is kind of a difficult idea, okay? And I have a thing I want to try here real quick. I don't know if this works or not. Do you know how to make videos with your Chromebook? Or your cell phone? Yep. So, cell phone or Chromebook, and we're gonna take a little field trip. It's kind of warm sometimes. So either whip out your Chromebook and set that up to make a forward-facing video, or a cell phone, or hopefully your buddy can hook you up here. And then I'm gonna take this guy. And this one. All right, just want to feel
Brought it to the big door. Oopsie, I left it there.
don't really be fun. He is the Bulgarian. What's measuring? Why? Like a lot longer All right, cool. So, what I need you to do
You
is
guys remember that, right? It's got a lot of resistance.
pop up your Chromebook there, and you need to get that video onto your Google Drive, your school Google Drive. Okay. So make that happen. How do you put a video on your school Google Drive? You hit share. Yeah? Do you not know how to like to your Google Drive, then you're good. Like, make that happen, and then I'll show you where we're going next. Eventually. If you can edit it and get it down to just the part where I drop the ball, it's probably best, but come on. There we go. All right, and then I just added this link up into the physics need to know. So on Canvas, this is up at the top, tippity tip top. Okay. So give this a sniff quick. We got about 5 minutes before you dip. Get it on your Google Drive, because then the link here that I just posted is going to kind of give you the next steps. This isn't homework. We're going to work on this in class tomorrow, but I need you to take a moment right now and try to get this all sorted out here. So just kind of check this out. At least the first video here. Hayden, can you be a hero and send that link of the video to me? Do you have the video somewhere? Yeah. You can send that to me somehow. Yeah. Is that doable or is it too big? Or if you want to just send me a Google Drive link.